we're just going to finish off with section 8.4. We're going to solve some word problems. Just want to remind you that our equation is typically AC to the power of BX. Remember that when you're looking at this, the A value is what you start with, because your y-intercept goes at 1, so the A value is going to stretch it to your starting spot. You can just write this somewhere at the top of your page, just this one. The B value is basically the change of time, because we said that the B value stretches your x-axis. So if your x-axis is taking place every 5 minutes, we've stretched it out to 5 minutes. Okay, so again, the B value is going to be the change of your time. And then the C, or the base, is what you're multiplying by. What you're multiplying by each time. So that's when we were in chapter 7. We discussed how to create some of these formulas with word problems. Now we're going to also solve those. Okay, example 1 says we have the half-life of a certain radioactive substance is 4.5 days. That means it's going to cut in half every 4.5 days. So, first of all, let's make up an equation for this situation. It says that we're starting with a 123 milligram sample. So I'm going to put that in for A. Since it's cutting in half, again, half-life means it's repeatedly multiplying by half. That means I'm going to put half in for my base. And then it says that the half-life is 4.5 days. That means my x-axis, instead of being 1 day at a time, is stretching to 4.5 days. But be careful, B is backwards. So if I'm stretching it to 4.5 days, it's 1 over 4.5, right? X, yep. So our equation would be this. Now also remember that y and your A value are related. So if I'm talking here that it's 123 milligrams, then y is also talking about the milligrams of the sample. So how much is left after x days? So for the first part here, it says how much is left after 7 days. So the 7 is x, yep. And this is now the exponential solving. So this is more like chapter 7, where we plug in 7 for x. The 7 will have to get divided by the 4.5 before we apply it as an exponent to the power to 1/2. So that'll give us a power of 1.56. Then I have to put half to the power of 1.56 before multiplying it by 123. Because BEDMAS says we do exponents before we multiply. So when you've done that, you should get 41.7 milligrams would be left of your sample after 7 days.
Actually, 40.
So part B is different because this time I'm looking for x and 15 is getting plugged in for y. So 15 equals 123. The base is half, and then it's 1 over 4.5 to the power of x. This time I'm looking for x. So this is an exponential equation, but I can start by making it easier on myself by dividing that 123 over to be with the 15 before I start solving it. So 15 divided by 123 gives us approximately 0.12. And I'm also going to write my half as a decimal. And again, this is going to be 1 over 4.5 times x as my exponent. Now, when we're solving something like this, remember you have 3 options. You look, okay, are there logs on both sides, logs on one side, or are there no logs at all? No logs at all. So to solve this, I'm going to put a log in front of both sides. How does that help us? Because now my exponent can go to the front. And now that my exponent is moved to the front, remember that log 0.12 and log 0.5, those are just numbers that I can calculate with my calculator. It would first be good to divide the log 0.5 to the other side so that I have my x part here by itself. So on the one side, when we take log of 0.12 divided by log of 0.5, we get 3.05. And then all we have to do is multiply out that 4.5 to get an answer of approximately 13.8 days. We're talking here, x is in days. Our last word problem example is about population. So here it's saying the population of a city was 115,000 on January 1st, 1990, and then 130,000 on January 1st, 1995. Assuming the exponential growth, what was the population on January 1st, 2000? So this one is a little bit tricky because I don't know my exponential growth rate. So here we don't know our base. So we're going to plug in kind of a coordinate that we know. We know that after 5 years it grew to 130,000. So I'm going to plug in 130,000 for y and then 5 for the x. Now I'm going to solve this to find the base because first of all we need to find the base to find this equation. So I can start by dividing out the 115,000 and we get 1.13 approximately, which equals c to the power of 5. Now this is where you said, can't we quintic root it? Yes, because how do you undo a power of 5? You fifth root it, right? So we're going to put these both to the fifth root, and when you fifth root 1.13, you get 1.02 equals your growth factor. What that means is that we're growing at 2% each year. Because remember that you go 100% and then it's on top of that another 2%. So you're growing 102%, which means it's an extra 2% each year. So now we know that the growth is 2% each year, so I can say that my general form is 115,000 times 1.02 to the power of x. Now to answer our actual question, what will be the population in January 1st, 2000? That means I'm going to plug in x equals 10 because 10 years have passed since 1990. So we just plug in 10 for the exponent of x. Then we go 1.02 to the power of 10, multiply that by 150,000, and you should get the population would be 140,184 approximately in the year 2000. So for part B, now we're saying when is the population 200,000? So 200,000 is y. So into my equation, I'm going to put 200,000 equals 115,000, 1.02 to the power of x. To make this easier on ourselves, so let's divide out the 115,000 first. So we get 200,000 divided by 115,000. I got approximately 1.74. And again, that equals 1.02 to the power of x. How do I solve when there are no logs? Put the logs in front of both. Yes. So I'm going to put a log in front of both. And that helps now because now my exponent can go to the front. So what you'll get here is log of 1.74 equals x times log of 1.02. So again, that exponent is going to come to the front. And now we really just have numbers. But I want that x to be by itself. So let's move the 1.02 to the other side, the log 1.02, sorry. And when you divide out log 1.74 by log 1.02, you should get approximately 28. So in approximately 28 years from 1990, it would be 200,000 people. So that would be the year 2018. Right? 2018. Okay. Yeah.